Good evening, everyone. So let's start doing some examples of body plots. So this is one of those things that practice, where practice makes perfect, really. So the more practice we go through, the better you would get at drawing those body plots. And the nice thing is that you can always, of course, compare your body plot sketches to what you can get from MATLAB or Simulink. So let's do an example. Example is as follows. Oh, it's doing handwriting recognition. I don't know why. Okay, GVS equals 25 S plus 1 over S squared 0.1 S plus 1. So this is a transfer function where the poles and zeros are in normalized form. And remember that S is a shorthand for J omega. Right? So here we have a constant. We have two poles at origin, meaning at S equals 0. We have one pole at tau equals 0.1, meaning omega equals 10 rad per second. And then we have one 0 at omega equals 1 rad per second. Right? Okay. So yeah. So we want to start by plotting each one of those separately and then combining them, adding them together. So let me do that. Let me actually do the x-axis. Right, so I have the x-axis and the y-axis. So I have the x-axis, which is log omega. And then I have the y-axis, which is the magnitude in dB. So I'm going to start with something like this. Oh, let me do 90 degrees actually. Make sure I'm at 90 degrees. Right, so this is the magnitude of h j omega in dB. Okay, so the simplest thing, of course, is going to be the 25. The 25 in dB, the constant gain in dB, what would it be? It would be, so let's do it down here. So it's going to be, the gain K in dB is going to be just, this is in dB, is going to be just 20 log 25. So it's just a matter of calculating this to determine what the gain would be. And we're going to start with the gain. Alright, so let me see what the gain would be. Calculate the gain, I'm moving to Mathematica. So if I do 20 log, in Mathematica, log, by the way, is log to the base e. So if you do log 10, you don't get 1. So let me see, let me get the value. You get 2.3, so this is log to the point e. To get log to the base 10, you need to do log 10. And this is something you have to check in MATLAB too if you're using MATLAB. I don't recall in MATLAB if the log is to the base 10 to the base e, but the point is that it might be to the base e. When we are doing those body plots, we are always doing the log to the base 10, right? So to do, so yeah, what I'm trying to find now is 20 times log to the base 10, log 10, and then 25. So when I do that, and I need to turn this into a numerical value, I get 27.958. So that's the value of the constant gain in dB. All right, so we know this is equal to now 27.96 dB, and that would be let me draw the gain here. So that will be, well, let me designate each 4 blocks to be 10. So 1, 2, 3, 4, that's 10 dB. This is 1, 2, 3, 4, that's 20 dB. 1, 2, 3, 4, that's 30 dB. So 27 will be 25, 26, 27, 27 and a half. So each small rectangle square would be 2.5 dB. So 2.5 plus 5 is 5. 7 and a half. So it's going to be about here, right? So this is where the gain would be. Let me draw it as a dotted line. This is not the whole body plot. This is just the body plot due to the gain. And it's something like this. It's a straight line. Okay, so this is the gain K. Now, what's the next thing we want to plot? Well, let's start with the 0. So we're starting with, actually, let's start with the double pole at the origin, because one easy method we can use is we could always move from the one with the lowest frequency to the pole or 0 with the highest frequency. So the frequencies in this case are 0. We have poles at the origin, and then we have a pole at 1 rad per second. So 0 rad per second, and then we have a pole at 10 rad per second. Right, so we wanna start. I don't know why it's doing that. Oh, I have ink to shape selected. Okay, so 0 rad per second, 1 rad per second, 10 rad per second. So let's start with the 0 rad per second. I have s squared. What does that mean? What does s squared mean? Well, s squared means I have a straight line, right? That's what we said a pole at 0 is. A pole at the origin is, but we have squared, so that means that the slope of the line is going to be 40 dBs per decade. I have to determine now what my x-axis will look like. So this is now, the origin is going to be at log 0 equals 0, which is equivalent to 1 rad per second. Undo. So this is equivalent to 1 rad per second. And then I'll select it such that every 5 squares is 1 decade. So this is going to be right. Let me actually make it wider. So let me select every 10 squares. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 rads per second, right? Let me delete this. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 100 rads per second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 1000 rads per second, and so on and so forth. All right. So what we know is at 0 there is going to be, and I might have to actually give myself some space here. So let me take this and move this away. Right. So I want, let me change the color to blue. And then we said we wanted to draw a straight line that's 40 dBs per decade. So so that means I have to extend this axis. Let me go to black. So I'll extend this axis down here. Let me erase this. So each 4 blocks is going to be 10 dB. So this is 10 dB, 20 dB, 30 dB, right? So each 4 blocks is going to be 10 dB. So it's going to be 1, 2, 3, 4. That's minus 10. 1, 2, 3, 4. 1, 2, 3, 4. That's minus 20. 1, 2, 3, 4. That's minus 30. 1, 2, 3, 4. That's minus 40. Okay, so that's enough. I need to have enough slope to give me 40 dBs per decade. So this is 40 at 10. So this goes here. So this is the other point. So this is at 10 rads per second. I have minus 40. I just now have to join between those 2 points to get the minus 40 dB per decade slope. So this is the gain due to the, right? This is now due to the 1 over s squared. Okay, so we are done with this. Now what's left? What's left is the pole and the zero. So the zero comes first, happens at 1 rads per second. So let's start with the zero. So the zero, let me go to green for the zero. So the zero has a corner frequency of 1 rads per second. So the zero, starts at 0 dB, as we said, as we derived last time. And then at 0, it goes up with a slope of what? 20 dBs per decade. So at 20 dBs, after 1 decade, I have to go by 20 dBs. So I should be here, right? So if I do that, this would be the 0. It goes up like this. Right? And it happens at 1 rad per second. Now there's a pole that's happening at 10 rads per second, right? Tau is 0.1, so inverse of tau is going to be 10, right? So this is a pole. What does it mean to have a pole? I don't know what color should I choose. I guess I'll choose red again, right? So the pole happens at 10, so it's here. So the pole is like this. And then at 10, it goes down minus 20 dBs per decade. So at 100, it should hit minus 20 dB. So at minus 20 dB at 100 is this point. So we should go down with a slope like this. So now we have all the information to plot the complete Bode plot. For me to plot the complete Bode plot, I guess let me go back to black, right? And then plot everything. So I'm gonna use the technique of starting from the lowest possible frequency to the and moving along from the lowest frequency to the highest frequency, and then start with the gain, draw everything around the gain, and then move along the gain. So I'm going to start with the 27.96 gain, right? So the first frequency that I encounter is 0, right? Because I have double poles at 0. So I'm going to start with my equivalent curve. So I'm going to start with the gain and move all the way until I draw a line until I get to the first frequency in my Bode plot and my transfer function, which happens as 0. I have a double pole at 0. So I draw the straight line like this. Let me draw it. Okay. Actually, let me see if I can increase the width of. Can I increase the width of my? I don't know. Oh, perhaps I can. So let me increase the width so that it's clearer what we are plotting. Okay, so this is, yeah, this is better. I mean, it might be too wide, but that's fine. Okay, so yeah, so this is now at 0. I'm going to go down minus 20 dB, minus 40 dB per decade. Right? So oh, now something interesting happens at 0. I'm going down minus 40 dB per decade due to this, right? But then this double pole. But then I'm also going up plus 20 dB per decade due to the 0. So I'm going down minus 40, going up minus 20. So I'm equivalently going down minus 20 dB per decade, right? Up until I hit 10, I should go down minus 20 dB. So I go down up. This is 110 dB. This is minus 20 dB. I need to hit this point. This is 20 dB below that point. Right? So I end up. So see, the point here is that instead of going down at minus 40 dB per decade, because of the existence of the 0, it kind of reduces that slope, and now I'm going down at minus 20 dB per decade. Right? So this is minus 20 dB per decade. Right? And so this kind of like 0 moderates this double pole. Right? Now after 10, I have a pole that occurs. So now another interesting thing happens. Now I don't have just the double pole. I have the double pole minus 40 dB per decade, but then I have an extra pole, right, which introduces another minus 20 dB per decade. So after 10, I should expect the slope for the poles by themselves to be minus 60 dB per decade. But I still have the 0. So minus 60 minus plus 20 is going to be minus 40 dB per decade. So now in the next decade, the slope is going to not be minus 20, it's going to be minus 40. So I need to go down by 40 dBs. So I start here, I go down 10 dB, right? 1, 2, each 4, let's see, each 1, 2, 3, 4, 1, 2, 3, yeah, each 4 blocks is 20 dB, 10 dB. So this is 1, 2, 3, 4, 10, 1, 2, 3, 4, 20. Oh, sorry. 1, 2, 3, 4, 20. 1, 2, 3, 1, 2, 3, 4, 30. 1, 2, 3, 4, 40. So now I'm going with double the slope. I'm going down this way. And this is what the magnitude plot would look like. This is it exactly. So I'm going to start with the gain, constant gain. At 0, I have rad per second. I have the double. I have 0, and I have the double pole at the origin. So effectively, I'm going to have a slope of minus 20 dB per decade. But then after 10, an extra pole kicks in, and my slope increases by an extra minus 20 dB per decade. So this slope here is minus 40 dB per decade. Okay. And this is what the magnitude plot is going to look like. Now we want to plot the phase, and we're going to use a similar strategy to plot the phase. Oh, sorry, by the way, I made a mistake. The double pole at the origin does not start at 0. It exists everywhere. It exists for all frequencies. So really, although at 1 rad per second we're starting with the gain, right? But the double pole exists everywhere. So what we need to do is we need to have, let me erase this, we need to have the minus 40 dB per decade of the double slope existing before 1 rad per second. So if I go here and do like 1 decade, I said 1 decade is 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 0.1 rad per second, right? So at that point, I have what, minus 40 dB, so it's going to be 1, 2, 3, 4. 1, 2, 3, 4. That's 20. 1, 2, 3, 4. That's 30. 1, 2, 3, 4. That's 40. So it's going to be this point, right? So it's going to be something that looks like this actually. So it's going to be something with a slope of minus 40 dB per decade. Okay, so this is the correct magnitude response, right? Because before, under 1 rad, my mistake was that under 1 rad per second, I already considered the gain K. But there's not only the gain K, there's the double pole at the origin exists, right? So we start with the double pole, which is minus 40 dB per decade. And then once we hit 1 rad per second, that's when the zero acts up. It reduces the gain. But then at 10 rad per second, we have an extra pole, which brings back the gain, which cancels the effect of the zero, essentially, and brings back the gain to minus 40 dB per decade. So this is the correct magnitude response. Okay. So now we said we wanted to do the phase. So to do the phase, actually, I need to reduce the width of the line again, right? So I just now I want to do the phase. So let me go down here. Now, as far as the gain is concerned, the gain is not going to introduce anything to the phase. That's simple. The only thing that's going to introduce anything to the phase is going to be the poles at the origin and the poles and the zeros. So let me replicate the plot just so we can do the phase. Let me do it down here. So let me draw the x-axis, log omega. What would the frequencies of interest be while we're doing the phase? Remember, so when we're doing the phase plot, the frequencies of interest are always going to be the pole and zero frequencies, but also we'll be interested in 1 decade above and 1 decade below, right? So we'll be interested in 1 decade below 1 rad per second, which is going to be 0.1 rad per second, and then we're going to be interested in 1 decade above, which is 10. For 10 rad per second, we'll be interested in 1 decade below, which is 1, and then 1 decade above, which is 100. So I think we can easily just copy the same thing, right? So yeah, I think it's fine to copy the same thing. So I'm gonna do this, and then I'm gonna, I guess, start with 1 here. This is the y-axis. Then I want to plot the whole thing, right? I want to give myself a lot of space for negative and positive angles. Right. So this is going to be 1 rad per second, and we said we wanted every 10 blocks to be 1 decade. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 100, so on and so forth. And then I'm interested in 0.1. So it's going to be 10 blocks behind 1. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be 0.1. Okay, and then I don't know, maybe we can do right. So s squared is we're gonna start with of course the constant is a phase of 0, but s squared, which is the double zero at a double pole at the origin, is gonna give me a phase of what, minus 180 degrees, right? Each pole is gonna give me minus 190 at the origin. So the total is going to be like a constant minus 180. So you're starting with minus 180. I guess what we could do is we could do I don't know. Let's select each 10 blocks to be 45 degrees perhaps. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, each 10 blocks, let that be 90 degrees. So this is 90 degrees minus 90, and then the other 10 blocks is going to be minus 180. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's minus 180. Oh. And then above, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's positive 90. And then 10 above is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be 180. All right. So we have double poles at the origin. So we have a constant minus 180 everywhere for all frequencies. So we have this. Okay. And then we have a pole and a zero. And again, let's follow the process of starting with the lower frequencies and moving up. So starting with 1, we have a 0 at 1. What does that entail? Well, we have to pay attention to 2 inflection points. We have to pay attention that what happens 1 decade below and 1 decade above. And let me move to blue. So 1 decade below, we're gonna, this is a 0, right? So we're gonna start at 0 degrees. Right? And then 1 decade above, we're gonna go to 90 degrees. And the angle is gonna be 45 degrees per decade. So we're gonna have 2 decades, which will take us from 0 to 90 degrees. So this is the characteristic of the asymptotes for the 0. It's gonna look like this. I'm just drawing the asymptote now for the 0. Okay, so this is the 0. We're done with the 0. Now let me move to the pole. The pole is at 10 rads per second. So the 2 inflection points of the asymptote are going to be 1 decade lower and 1 decade higher. So again, the pole is going to start with 0 degrees for the phase, and then it's going to go to minus 90 at 100. Of course, with the slope of minus 45 dB per decade. So it's going to look like this. Go down to the slope of minus 45 dB per decade and then settle at minus 90. Right? Now getting the final phase plot is just a matter of, so this is phase Hj omega. It's just a matter of summing all those different plots together. Let me increase the width of the line so that things are clear. Right? So up to point 1, we have a constant of minus 180. So up to point 1, we're at minus 180. Right? What happens after point 1? Well, we have from point 1 to 1, we have 1 decade, and during that 1 decade, the 0 starts acting up, right? And then we have an angle of 45, a slope of 45 degrees per decade. So we should, within that 1 decade, hit 45 degrees. So we should hit the midpoint between minus 90 and minus 180. We should hit minus 90, minus 45, which is minus 135. So this is 1, 2, 3, 4, 5. This is minus 145, sorry, minus 135. Let me write it. Okay, and this will be like this. So that's the slope of the 0. Now in the second decade, from 1 to 10, we still have the slope of the 0, but now the slope of the pole starts happening and it counteracts the slope of the 0. So we have here plus 45 degrees per decade, and we have here minus 45 degrees per decade. So we end up with an effective slope of 0. So up to 10, the slope of the phase is going to be 0. Right? And then after 10, the 0 is going to settle to a constant, right? And then the pole is still going to continue. So the pole is going to continue with a slope of minus 45 dB per decade, right? So after 1 decade, we're going to go back minus 45 degrees. So we're going to go back to minus 180. So that curve is going to look like this. And then there will be there won't be any slope anymore. So we will go back to minus 180. And this makes sense. After 100, if you sum all the phases, it's going to be plus 90, minus 90, which is 0, and then minus 180. So we settle back at minus 180. So this is what the phase response for this example is going to look like. Okay? Okay, so now we want to do another example. Oh, let me return this to... Okay, so I want to do another example now where we want to look at the Bode plot and try to deduce the transfer function from that Bode plot. So let's say you see a magnitude response like this. It should be clear from the magnitude response what is happening as far as the poles and the zeros, right? The first thing we could notice is that we're starting with 20 dB per decade, right? Sorry, 20 dB. So that's our starting point. Typically, if the gain is 1, the gain in the transfer function, so we have some k0, and then I have the zeros, and then the poles, right? If the gain is 1, I will start at 0 dB, because I'm starting at 20. That means that 20 log the gain is going to be 20, right? So 20 cancels with 20. That means log k0 is 1. So take 10 to the power on both sides. We end up with 10 to the power log k0 equals 10 to the power 1. So we end up 10 to the power is the inverse of the log. So we end up with k0 being 10. Right? So the first component of the transfer function is going to be 10, constant gain of 10, and then we're going to have the poles and the zeros. The poles and the zeros are easy to determine from the Bode plot. So notice here we have a corner frequency here happening where? Well, this is happening, let me take the ruler. This is approximately happening, I would say, yeah, this is all approximate. I think it's happening approximately at 0.1, let's say. Okay, so it's happening at 0.1 rats per second. So this is, and then after the 0.1 rat per second, we are going down by minus 20 dB per decade. So there is a pole at 0.1 radians per second. Notice that this minus 20 dB per decade slope stops at so this is 0.1, because this is, by the way, a logarithmic x-axis. So this is going to be 0.1, this is going to be 0.2, this is 0.3, this is 0.4, and then at 5, tick 5, this is going to be 0.5. So there is a 0, right? There has to be a zero at that frequency at 0.5 radians per second, because that's the only way to counteract the pole, right, and to stabilize the slope. So the slope goes, the only way for the slope to go from minus 20 dB per decade to 0 dB per decade is to have a zero that counteracts the pole. So we should have, after 0.5, at 0.5 we should have a slope after that of 20 dB per decade, which counteracts the pole, and we end up with stabilizing the pole, right? So there has to be a zero at 0.5 rads per second. Okay, we continue. Nothing is happening up to this point here is 1 rad per second, and then this point here is 3 rads per second. At 3 rad per second, we continue going minus 20 dB per second per decade. So at 3 rads per second, there has to be another pole. Okay, and then we continue going minus 20 dB per decade. But then we go another minus 20 dB per decade, and the slope doubles to minus 40 dB per decade. This is happening at, so this is at 10 rads per second. This is at 20 rads per second. Right? So there is an extra pole now at 20 rads per second. Okay, and that's it. It continues after that. So now we've determined all the poles and zeros of this system. We have 3 poles and 1 zero, and that's all the information we need, right? So 0.1 rad per second, so that's the pole, that's the omega, right? So what's the tau? Tau is going to be equal to 10, right? So this is going to be equivalent to this pole, 1 plus 10s, using the normalized form, right? And then we have the we said 3 rads per second. Is there a 3 rad per second pole here? Did I make a mistake? Yeah, there is a 3 rads. So this is 1, and this is 2, and this is 3 rads per second. So there is a pole at 3 rads per second. So the tau in this case is 1/3. So this is going to be 1 plus s over 3. And then there's a pole at 20. So this is going to be a pole of 1 plus s over 20. Okay. And then there's a 0 at 0.5 rads per second. So this is going to be a 0 of 1 plus s over 0.5, which is going to be 1 plus 2s. So let's combine everything. H of s equals 10. The gain is 10. And then we have a 0 at 0.5 rads per second. 1 over 0.5 is 2. So it's going to be 1 plus 2s. And then let's do the 3 poles. So the first pole is at 0.1 rad per second. So it's going to be 1 plus 10s. The second pole is going to be at 3 rads per second. So let me just write it 1 plus s over 3. And then the third pole is at 20 rads per second. So this is going to be 1 plus s over 20. And this is it. This would be the transfer function that we can deduce from this magnitude Bode plot. Notice we don't need the phase to determine the transfer function. We could determine that information from either the phase or the magnitude. The magnitude by itself is enough for us to determine the transfer function. Okay, so yeah, with this, I mean, this is the material I want to cover in this chapter. The rest of the chapter, I'm gonna, I mean, the most important topic in this chapter is Bode plots, because it allows you to, gives you the proper tool set for you to plot the frequency response for any circuit, right? The rest of the chapter is a bit about physics oriented, with the discussion of resonance. Right? And I'll leave that as reading material for you. I will not include any of that in the final exam, but I encourage you to go through that material for your own education. But the subject of resonance is more of a physics oriented interpretation of what we already know, which is how to analyze RLC circuits. There's nothing new there. It's just we analyze those circuits from a physics perspective by introducing what's called the Q factor. The Q factor is a way for us to quantify, if we plot the frequency response of this RLC filter, let's say the impedance looks something like this. It's a way for us to quantify how sharp the bandwidth of this RLC filter is. So when we plot the body, do the body plot or the frequency response, the sharper the response, the higher the Q factor. The Q factor is essentially an energy measure. It measures, it represents a measurement for an oscillator. So that's what a resonance circuit is. It's an oscillator, right? And whenever you have something that oscillates, after each oscillation, there's a bunch of energy in the system that keeps wobbling in the oscillation. It keeps going back and forth. But with each oscillation, there's a portion of the energy that gets lost, right? In the resistor, let's say, in this example. Or in the mechanical system, it's not particularly have to do with a RLC circuit. It could be any oscillatory system, right? So the key thing is that with every oscillation, there's a portion of the energy that's lost. Now, the portion of the energy that is lost with respect to the full energy of the system, of the oscillation, is what the quality factor measures, right? So that's what all of this is about. There's nothing new there, rather than it being a physics-oriented way of understanding RLC circuits, right? And then the other topics after that are scaling and filter networks. And again, filter networks there's nothing new there. We already know how to do a low pass filter, right? It's an RC, right? And then we know how to do, right? Why is this a low pass filter? Even without writing the equations from inspection, at high frequencies, the impedance of the capacitor is going to be 0, right? So VO is going to be a short. This is a high pass filter, right? And then a band pass filter, so this is a low pass filter, high pass filter, and then a band pass filter is just an RLC circuit, something like that. Okay. So this is a band pass filter. It will look at this frequency response if you plot it, depending on what you consider the output to be, right? It will either look like this or it will look like this. Okay. It will either pass a certain frequencies range or suppress a certain frequency range. For example, what would happen, so if I have, let's reason about this. If I have a resistor, an inductor, what happens if I have an inductor and a capacitor? What's the impedance of this thing? The impedance of this thing is is SL, and this is 1 over SC, right? So if I plot the frequency response at low frequencies, the impedance of the inductance is going to be, this is the impedance of this whole thing, plus Z, right? So the impedance of the inductance will dominate at low frequencies. Will be close to 0 at low frequencies, right? And then it will go higher at high frequencies. For the capacitor, the impedance will be short or small at high frequencies and high at low frequencies. So effectively, the effective impedance is going to look something like this. So there is going to be a point of minimum impedance, right? And then at high frequencies, the capacitor is going to dominate. So this is where the capacitor dominates, and this is where the at low frequencies the capacitor has a very high impedance. So this is where the capacitor dominates, and as the frequency gets higher, the capacitor turns into a short circuit, and this is where the inductor dominates. So the impedance, when we plot it versus frequency, is going to look something like this. Okay, and this allows us to kind of like build a bandpass filter, right, using this basic LC combination, right? Because if we do this configuration, right, and this is Vn and this is plus minus Vo, what happens here is that at a certain frequency range, the impedance is going to be minimum. So that means the gain is going to be minimum, GV, this is Vo over Vn. It's going to be minimum at a certain frequency range, and then the impedance goes higher while we're outside that range, so the gain increases. So this is what's called a notch filter, meaning the gain is minimum at a certain frequency range, right? If we do the opposite, and then we pass the low frequencies and the high frequencies. This is an example of a notch filter. And then if we do something like this, we do L, C, and then we do R, and this we have Vn, and then Vo. This is an example of a bandpass filter, right? So the impedance for a certain frequency range, the impedance is going to be minimum here, so that the voltage divider is going to maximize the voltage with respect to the input. So the gain, Vo over Vn, is going to be maximum in this frequency range. At high frequencies and low frequencies, this impedance will be maximized. Therefore, the transfer function, the voltage divider, is going to be minimized. So the gain is going to look like this. Okay. So this is briefly how we can build different kinds of filter networks. Right? In reality, I mean, we don't, in many applications, it's okay to do filters simply like this. But filter synthesis is a little bit more complicated and involved subject than just using simple resistive elements and passive elements. So for filter synthesis, people start using op amps, right? Stuff like this, right? And use they connect multi-stage op amp circuits with passive components to build more complicated filters. Those examples that I've shown you here are only the simplest kinds of filters that you could build. You could build more complicated, higher order filters, and it's a big topic called filter synthesis in analog circuit design. Okay, so this is a big topic, and I mean, in this course, even that chapter in the book only touches briefly on it, right? So I recommend you kind of read quickly through that chapter, right? But having said that, the most important part of this chapter is the Bode plot technique. So I would rather you spend time practicing this technique of plotting the frequency response. So now we want to move on to the more important topic, which is the Laplace transform and its application to circuit analysis. So over the next perhaps 4 or 5 lectures, I want to focus on this topic, and with this topic we will end our network 2 course. Right, and this is a beautiful topic. This will be like the crowning discussion in this course. This will be interesting. So yeah, so we'll start this over the next lecture. Thank you guys. See you next time.